So thank you to the organizers for the opportunity to speak here today. I'm going to tell you about some joint work with Emanuele De Lucchi, who's based in Switzerland. And this is an outline of what I'm going to tell you about. So we've seen hyperplane arrangements come up a few times this week. And I'm going to tell you about a toric analog and some of the combinatorics that we get from these toric arrangements, which I call locally geometric posets. So these are not lattices, but they're things that kind of locally look like geometric lattices. And I want to tell you about what it means for these things to be supersolvable. So I'll first tell you what Stanley says it means for a lattice to be supersolvable, or really just what it means for a geometric lattice to be, and then how we can extend it to our setting. And an even stronger condition where we can get some nice combinatorial consequences on the characteristic polynomial, and then a topological consequence at the end. Okay. So here's some information about hyperplane arrangements. So a hyperplane is just a solution set to a linear equation. And I'm working in Cn. And a hyperplane arrangement is just a finite set of these hyperplanes. And so I have an example. Let's see. It is. Oh, there we go. OK. So I have this example. So I wrote here like the 3 normal vectors for different lines inside of C2, and I drew the picture over here on the left. So I actually drew R2 instead of C2 because it's a little easier to draw, but it's going to capture the same combinatorics. So the vector 1, 0 is going to give me the line x equals 0. Then I have y equals 0 from the second vector 0, 2. And then I have y equals 2x from the third one. And the combinatorics we associate to this is looking at how these hyperplanes intersect each other. So this is the poset that I denote P of A over on the right. I'm looking at all of the intersections of these hyperplanes, and I order them by reverse inclusion. So I always have at the bottom the ambient space. If I intersect none of the hyperplanes, I get the whole space. Reverse inclusion means that's the largest subspace, so it's the smallest thing in my poset. And then I have each of the lines themselves. So I've color-coded them, red, yellow, blue. And then any 2 of them or all 3 of them all intersect at the origin, so that's my largest thing in this poset. And this has the structure of a geometric lattice. I will write down a definition of that later, but if you're a matroid person, this is always the lattice of flats of a matroid. And the one kind of thing that I did a little funny is I restricted myself to normal vectors with integer entries. And I did that for this toric analog because I can kind of analogously define solutions to an equation on a torus which looks like this, where now I think about the multiplicative group structure on C star. So when I see something like 1, 0, I want to look at this as an equation as x to the 1 times y to the 0 equals 1. So that gives me in a torus, and again, I can't draw C star squared, so I drew S1 squared. So these are opposite sides of this rectangle are glued together. And this x equals 1 is a subtorus coming from this first vector. Then I get y equals 1 for the second one, and then this gives me an equation that looks like x squared y to the minus 1 equals 1. Which is a y equals x squared, and this kind of wraps around the torus twice. So it's that blue circle that's wrapping around the torus twice. And here, the kind of funny thing that happens is that these intersections are no longer connected necessarily. So I'm going to look at the connected components of those intersections instead of just the intersections. So I still have kind of at the bottom my torus. It contains each of these subtori in my arrangement. But then I see that at this point, all 3 of these little subtori intersect at that point, so I get this. But then the blue and the yellow intersect also at this point, so I have another point there that's contained inside of the blue and the yellow. Okay, so I get some kind of poset like this that captures the intersection pattern of this arrangement. And it's not a lattice, because this blue and the yellow, they have 2 connected components of their intersection, so there isn't a unique least upper bound. And similarly, these 2 points are contained in both of blue and yellow, so there's no greatest lower bound for them. But we do have this kind of nice local structure where I can look around this point, and in a little neighborhood here, what I see are 3 lines intersecting at a point. And so in the poset, what I see is that if I look at this point and all of the stuff that contains it, so I've kind of pictured that over here, what I see is a geometric lattice, and actually this one, because it looks like 3 lines intersecting at a point. And similarly, if I look around this point, I see 2 lines, a yellow and a blue, intersecting at that point. And so looking kind of underneath that point in the poset, I get this geometric lattice. Okay. So these are the kind of posets that I get. I have a little bit of notation that I want to introduce. Because I don't have unique least upper bounds or greatest lower bounds, I want to actually look at the set of minimal upper bounds and the set of maximal lower bounds. So that's how I'm going to be using this notation. And then, of course, it's a lattice if I actually have a unique thing in each of these. So I have a picture of a lattice over here. This is a semi-lattice because it has a unique meet, but not necessarily joins. And then this is the example that I was talking through on the last slide, that B and C have both U and V sitting above it, and U and V have both B and C underneath it. But then I also have things like A and V. They don't have a common upper bound, so I can write that as that A joined V is the empty set. Okay. And from this, so just a reminder of what a geometric lattice is, and what I was hinting at on the last slide, a locally geometric poset is really a poset where all of these closed intervals are geometric lattices. And I am also going to require that it has a unique minimum element. So that's kind of depicting the fact that all of these things in the arrangement are contained inside of an ambient torus. Okay. So this contains geometric lattices, of course, are all examples. This is an example of a geometric semilattice. So geometric semilattices are also locally geometric. And simplicial posets, so this is also an example of a simplicial poset. What it means to be a simplicial poset is all of the closed intervals are Boolean lattices, and Boolean lattices are, of course, geometric. And then this is the example that I had on the last slide that has this kind of geometric lattice here and geometric lattice there, and then a new one that will come up later. Okay. So what it means for a geometric lattice to be supersolvable, I first have to tell you what it means to be modular. And this is best seen through some non-examples, so I have to give you a slightly larger example of a geometric lattice. This is a partition lattice, so partitions of 1, 2, 3, and 4. And there's a lot of different criterions about modular. This is just kind of one that I picked out, but there's at least 10 different equivalent conditions that I could have chosen from. So what it means to be modular is that if I look at all of the complements, so everything that meets it at the bottom and joins to the top, if they should form an anti-chain, so no 2 of them should be comparable. So I have a non-example up on the left. This thing right here, all of the things that are complements are highlighted in orange. So we have things like 1, 3. Well, they don't share any atoms, and their join is the top. But I also have, say, 1, 3, 2, 4, that partition, and this partition and this one, they don't share any atoms, and their join is at the top. But of course, this isn't an anti-chain because those are comparable. Okay, but something like the 1, 2, 3, and maybe I should have explained I'm using shorthand. If I don't write a number, that means it's in a singleton block. So this really means the partition 1, 2, 3 in one block, and then 4 by itself. So partitions like that are always modular. In this case, I highlighted their complements there. No 2 of those are comparable. So what it means to be supersolvable is I should have a maximal chain in the lattice that is made up of modular elements. So there's an example here on the right. The bottom and the top are always modular. You kind of get those for free. Atoms are also modular. And then I just told you that this one was modular. So this is a maximal chain in my poset, and every single one of these is modular, so that makes this supersolvable. And this was defined by Stanley. Okay. All right, but I want to make sense of this for our posets. And the difficulty is, the difficulty is that this definition of modular, or really looking at these complements, I don't have a maximum element. So I need to figure out how to make sense of a modular element, and really, I don't want to look at a modular element, but kind of find modular elements in all of these local geometric lattices that I have. But I need to do this in some nice compatible way. So I do this by looking at a particularly nice order ideal. So an order ideal is something that is down-closed. And I have some extra conditions that it should be pure, meaning the maximal ranks or maximal elements all have the same rank. Join closed, so that means if I have two things in there, everything in its join, so all of the minimal upper bounds should be in there. So here's a non-example of this. These two, this red highlighted thing is my proposed ideal. But the join of those two maximal guys is up here, and that's not in there, so this is not join closed. But if I add it in there, so if I look at this highlighted bit, it's no longer an order ideal because it's not down closed. If I just looked at this red thing, so just the bottom and this one atom, it's not an M ideal by these other conditions. So what needs to happen is if I had an atom that's not in this highlighted bit, like this guy on the right, and something in here, they need to have a common upper bound, and they don't. That's what the first condition says. But the second one is kind of the really crucial one of trying to compatibly get these modular elements in all of the lattices, is that I want to look under this maximal guy, and I want some maximal thing in this highlighted guy underneath it to be modular. And I drew kind of a dotted line here because it's not under there. So I don't have a nice modular element from this ideal in that lattice. But if I looked at this highlighted bit, it will be an M ideal, because inside of this geometric lattice, I get this modular element, and inside of this geometric lattice, I get this modular element. Okay. All right, so this is what we call an M ideal. And maybe going back to this picture, I kind of color-coded this. So here's a modular element, and I drew its principal order ideal, so all of the stuff underneath it. Here's the next modular element, and colored in blue is all of the stuff underneath it. And so when you're in a lattice, of course, this idea of being join closed means that you should be a principal order ideal. So in a lattice, a join closed order ideal just means that it's a principal order ideal. This first condition is meaningless, and all I really need is a principal order ideal with that modular element at the top. So instead of thinking about supersolvability as a chain of modular elements, I can think about it as a chain of M ideals. So here are some examples and non-examples of that. So this is a chain. I always have, for each of these examples, the bottom and the entire poset are M ideals, so I'm really just looking for an M ideal in rank 1, and these are highlighted here. This is the example that I gave before. And this is something that is not supersolvable. If I just had a single atom here and the bottom, then something like this will not give me a modular element inside of that lattice. Okay. All right. But there's an even stronger condition that we're going to need, which changes this idea. So this is saying that I need to have a common upper bound between an atom not in Q and something in Q. But sometimes it's nice when I have a unique least upper bound between these. So if I add that condition, this is what I get. I call a TM ideal. And then if my chain of M ideals is actually these TM ideals, I call this strictly supersolvable. So the only thing I changed is highlighted in this pink here. Instead of just asking for a common upper bound, I want a unique least upper bound. So this example is one of those that we've seen before. Because if I look at one of these atoms and one of these guys that's highlighted, there's a unique thing above them. Okay. But something like this is not strictly, so this was an M ideal, but if I look at this guy that's an atom not in there, this guy that's in there, they have two common upper bounds, minimal upper bounds. So it's not strictly supersolvable, but it is still supersolvable. And of course, if you're a lattice, this condition is meaningless, so strictly supersolvable and supersolvable are the same for lattices. Okay. But when we have this nice condition, we see a good consequence for the characteristic polynomial. So the characteristic polynomial is something you can associate to any poset that has a rank and a minimum element. And it's encoding these Mobius numbers, which we define recursively, by assigning 1 to the bottom element and then making sure that for everything else, if you add up everything below it, you should get 0. So here's my examples for these two posets that we've seen before. On the left, right, you start with a 1 at the bottom, When you go up, what I need is for this and everything below it to add up to 0. I have a 1 here, which means I need to add -1 for it to be 0. That's the same for all of the atoms. If I go up here, I want to look at everything underneath it. I see 3 -1s and a +1. That adds up to -2, so I need to add 2 to get 0. So I've decorated in orange here the Mobius numbers for all of those elements, and then I want to put those as coefficients in this polynomial. So this thing has rank 2. Down below we have rank 0, so I get a t² with a coefficient of 1. I have 3 of these guys, which give me a t to the 1 with a coefficient of -1, but then times 3 of them. And then up here I have a t to the 0 with a coefficient of 2 plus 1, which gives me this 3. And then kind of similarly over here, I get a t². I have 4 minus t's, and then I have a +4. Okay. And remember, the one on the left was supersolvable, but not strictly, and the one on the right is strictly supersolvable. And one key difference between these is that the one on the right factors nicely, and the one on the left does not. So when you're strictly supersolvable, the characteristic polynomial factors, and the roots are actually integers, which count the number of atoms that you gain as you go up this chain of M ideals. So like here, this M ideal contains 2 atoms, so that's one of these 2's. And then the whole poset contains 2 atoms that are not inside of that M ideal, so that's the other root too. But we really need the strictly supersolvable for this to happen. And this was one of the first things that Stanley proved for supersolvable lattices, is that the characteristic polynomial factors. Okay.
So this is independent of the choice of...
Yeah. Okay. All right, so you might wonder why I didn't just call this supersolvable instead of strictly supersolvable, and it's because there's a nice topological interpretation of supersolvable as well, which works even when you're not strictly. And this relates this idea of supersolvable to having fiber bundles on these arrangement complements. Let me explain this through some examples. So Terrell did this for hyperplane arrangements. He said that the intersection lattice for the hyperplane arrangement is supersolvable if and only if we get this kind of tower of fiber bundles. So here's the example that we saw at the very beginning, these 3 lines inside of C2. And this is the intersection pattern. And so what happens if I forget one of these coordinates, so here's C2, let me map down to C by forgetting the second coordinate. And I want to restrict this to the complement of the arrangement. So I want to look at everything that's not on one of these 3 lines. And the image of that is everything in C except for where x equals 0. So look at everything that is not highlighted. It maps to everything that is not highlighted down there. And what it means to have a structure of a fiber bundle, well, first of all, I should look above any point. So if I pick a point that's not 0 and I look above it, I want to know what are all of the y's that I can add to get a point in the pre-image here. And any y is fine except for y equals 0, because that's this yellow line I removed, and y equals 2x, which is this blue line that I removed. So above every point, what I see is C minus a yellow point and a blue point. That's not quite enough to be a fiber bundle. We really need kind of a neighborhood around here where it trivializes like this. But that's hopefully enough to be convincing. And what happens for these toric arrangements, here's our example of something. So maybe I didn't say this before, but this was not an M ideal because this yellow and blue intersect up here, and that's not above this red guy. And what we see down here is what happens is that this blue and this yellow, they intersect, but not inside of this red guy. So when we project, when we forget the second coordinate, so everything that's not on the yellow, blue, and red lines that I've drawn maps down to everything that is not this red point. And if I look above -1, what I see is I'm allowed to pick anything except for this one point, where yellow and blue both pass through, but above somewhere else, I see everywhere except for this yellow and blue. So I get different fibers, and that means it can't be a fiber bundle. And it's exactly that condition of being an M ideal, that these 2 guys, they intersect at some point that's not above there. But here are some positive examples. One of these, this first one, I just took this picture and I flipped it. So instead of forgetting the second coordinate, I forgot the first one. And then this one is I guess, this poset that we've seen before. That's strictly supersolvable. And this also gives us a fiber bundle. And the kind of topological interpretation of this supersolvable versus strictly is that this has one yellow and one blue, whereas this has one red and two blue. So it's the non-strictness that's giving me punctures of the same color here. So you can kind of get a topological interpretation of how this characteristic polynomial doesn't factor. But I think that's all I wanted to say, so thank you.
Much. Are there any questions for Christin?
So is the strictly supersolvable type going to be if and only if the characteristic polynomial factors? Or are there examples where it factors and it's not strictly supersolvable?
So I would expect there's polynomials where it factors but is not strictly solvable, strictly supersolvable. I mean, even for geometric lattices, there are geometric lattices that have a polynomial which factors but is not supersolvable. I don't think completely. Yeah.
So if I understood correctly, if you're supersolvable but not strictly supersolvable, then you have a tower of fiber bundles but no factorization.
Right.
Or at least not necessarily factorization. Yeah. So does that mean the Leray-Hirsch theorem doesn't hold?
Right. So what's happening is, so you can think of like the action of the fundamental group on this, on the homology of this fiber, and it acts non-trivially by permuting these points that are the same color. So there's this kind of non-trivial local system that you have to deal with. Yeah.
So in general, if you look at the characteristic polynomial for these toric arrangements, is that related to the geometry of the complement of the hyperplane arrangement?
Yeah, so I think we saw in Nick's talk the relationship for hyperplane arrangements. There's just a slight kind of change of variables. And there's something similar here. It's a little more complicated, but they're basically the same. Yeah.
So now that you have a generalization or a notion of supersolvable for toric arrangements, have you thought about freeness and the module of logarithmic derivations? I mean, maybe this is related to Sarah's question as well about characteristic polynomial factorization.
This is something I've been thinking about a little bit the last few weeks. There's, I think, 2 papers from 10 or 15 years ago that do something, but there's still a lot that's not known about freeness for toric arrangements.
For the talk. So do you expect, so I know that there's other classes of arrangements, I guess they're called abelian arrangements, where you have a different sort of, they wrap around a different space. Do you expect something similar to kind of happen in those cases?
We did prove it for those.
Oh,
yeah,
cool.
it just, for simplicity, I was only talking about tori. But yeah, for abelian arrangements, you have this same theorem. Yeah.
And the same notion of M systems, M ideals and all that?
Yeah.
Cool.
Yeah, so I mean, so instead of, so I replaced, so you could, right, so for hyperplane arrangements, you think of them in C star. For these, you think of, in C, N. Here you think of it in C star to the N, but I could pick any connected abelian Lie group. So something that looks like R to the P times S1 to the Q, and I can define the same, let me see if I can go back to where I did this. Yeah. So in the same kind of way that I defined these things, just use your group operation and look at the kernel of something like this. And yeah. And you're always, so these locally geometric posets that you get, or maybe I should, go back to this picture here. Anytime that you have something that, around a little neighborhood, what I see is a hyperplane arrangement, that intersection data is going to be a locally geometric poset.
So in the usual arrangement case, there's the case of graphic arrangements and there's a characterization for supersolvability. Can you do a similar thing for these toric arrangements, like toric graphic arrangements when they're supersolvable?
So for graphic arrangements, all of the intersections are connected, so it has the same intersection lattice, and it's supersolvable if and only if the graph is chordal. Yeah.
Let's thank our, are there no other burning questions? We can thank our speaker again.